Hi, I'm Rosa,
And I'm Yom. We're computer science PhD students at Vanderbilt University.
and today we will present to you our paper titled Pragma Interactively Constructing Functional Brain Parcellations. One of the prominent goals of human brain mapping is identifying brain regions that have similar roles in cognition and behavior. These regions are typically referred to as parcellations and the maps as atlases. With Broadman pioneering brain mapping, many researchers created various atlases in various modalities. Not long ago, atlases have become particularly popular for localization of activations using functional magnetic resonance imaging. These maps of functional brain organization, also referred as functional atlases, are usually derived at the population level. In other words, the atlas regions are designed to capture functional brain patterns that are shared in common across individuals. However, there is considerable variability in the functional subdivisions at the level of individual person. To study individual variation in cognition and behavior, we need ways to explore organizational differences that deviate from these average maps. With this goal in mind, we designed Pragma, an interactive tool that allows domain experts to do just this: modify a mainstream atlas to better map onto subject-specific scans. This process leverages existing population-based atlases, allows investigation of hierarchical relationships between brain regions, and supports domain-specific analysis methods. These analyses are based on an input fMRI scan. A little bit background in fMRI. fMRI is a non-invasive technique that measures blood oxygen in the brain as a proxy for neural activity. Each scan is volumetric snapshots of the brain taken at different time points. Each 3D volume is divided into tiny cubic regions called voxels. Each voxel represents a fixed spatial location, and the signal is the change in neural activation over time for that unique location. Parcellation through Pragma is an iterative process. Pragma initializes this process with an atlas of expert's choice and visually encodes the parcellation scheme as a hierarchical node link diagram. The user can modify their parcellation through this interactive tree where the decisions are guided by a set of linked and coordinated views. These views support time course data analysis for understanding homogeneity of parcels, the variability of the time series data, a functional connectivity chord diagram to investigate interparcel relations, and an orthographic slice-based view of their current parcellation to locate unique parcels.
The iterative process begins with this node link diagram, which is a hierarchical representation of an atlas. Within the parcellation scheme, each node represents a parcel. The atlas, whether anatomically or functionally driven, provides a strong prior to organization of the brain. On this node link diagram, the root node represents the whole brain. The next layer splits the parcels into the left and right hemispheres. And this layer of nodes shows 7 functional networks on each hemisphere as given by the starting atlas. From this point outwards, the nodes are color-coded by their network, and this coloring scheme is matched across all the other views on the interface. For each network, we apply agglomerative clustering to group temporally correlative voxels together as parcels. The leaf nodes of the diagram make up the current parcellation scheme. From here, the expert can steer clustering with 3 actions: expand, collapse, and merge. When the parcel has low similarity, the expand action splits it into more granular parcels. Conversely, collapse will redefine a parcel that does not need to be further split. And when 2 parcels have similar properties, they can be combined using the merge action. The expert modifies the parcellation scheme with these 3 actions using information from the following set of supporting views. First, we look at homogeneity, which is calculated as the average pairwise temporal correlation for each parcel. We encode homogeneity as the size of the inner circle for every node, allowing for comparisons amongst linked nodes. A good measure of functional correlation is time series similarity within a region. Since the time series signals represent neural activity change, if a region is functionally homogeneous, the time series signals from this region should be similar. Pragma supports analysis of signal similarity using a mean time course line plot with a standard error confidence interval. 2 parcels can also be compared at once, which is useful during a merge evaluation. While the homogeneity glyphs in the time course plot depict within-parcel properties, this core diagram allows the user to assess the functional connectivity between parcels. Functional connectivity is defined as the temporal correlation of every pair of regions, and it is used to measure coactivity of discrete regions during various brain states. The core diagram encodes the presence and strength of connectivity between regions. This view is designed to visualize the current parcellation scheme mapped onto a brain template. Every parcel is outlined by the color representing its functional network and is coordinated with the rest of the views in the interface. And here's the full interface of Pragma. Collectively, the visualizations guide the user through the iterative process of constructing parcellations. We will quickly walk through an example case that shows how a user may use the linked views to inform a merge decision. First, we can anchor this node and then see if there are any other nodes that are similar to it. Clicking on a second node allows us to directly compare the two. The time courses of both nodes are overlaid onto the line plot, where we can see that the signals have similar time courses. Looking at their functional connectivity, we see that these two parcels have similar connectivity patterns. And as seen in the orthographic views, the parcels are located in the same spatial proximity. These observations suggest that the two parcels are similar enough to be merged. After merging, two parcels are combined into one, and the new parcel's properties are recalculated, resulting in different homogeneity, time course, functional connectivity, and anatomical representation.
We consulted with domain experts at different stages of development, using their feedback to iteratively improve the tool. After the design converged, we conducted a user study with 4 domain experts over Zoom. In order to evaluate the design choices, intuitiveness, and effectiveness of Pragma, we encouraged free-form exploration of the tool with no time restrictions. The feedback was primarily positive, with users giving Pragma high ratings as a tool for subject-specific analyses. The ability to compare 2 parcels on multiple views at the same time was particularly well received. One expert noted that a search for valid cognitive relations through single-scan analysis was likely to result in inconsistencies, mainly because fMRI data is very noisy. Given the feedback that we received, we plan on addressing issues related to common sources of noise in fMRI data by visually conveying uncertainty as part of our design. Furthermore, we plan on making our system more extensible, handling various atlases, clustering algorithms, and similarity measures in order to better address demands from domain experts.
Thank you for listening.
Thank you.